Hello guys, welcome back to my channel, Maison African Motives, still working on engineering science N3. So there's a request that we have, we are going to work from this question paper, which was written in March 2018. And I always say about these question papers that they are very, very useful because most of the questions they are taking from these past exam papers and they're just repeating these questions. If you see how they are attempting to bring new questions out of the old ones, so it's very, very important that you understand how they used to ask these questions. So that's what we have, guys, working with X paper for engineering science N3. So like I always say, you must also be given the water and steam table, the steam tables. You must be given that. It's a booklet that you must be given whenever you are answering or you are attempting an exam for engineering science N3. So anyways, that's it, guys. As we know, the instructions and the information, you must be very, very careful on how you attempt your questions because you have the instructions. Anyways, we shall quickly rush through the questions. We've got the first question, which is on motion, energy, and power. That is the first part that we have. And the first question on 1.1, which is to state the difference between a vector quantity and a scalar quantity, and that is just 2 marks for that, guys. As we know, a vector quantity, it must have magnitude and direction, while a scalar quantity is supposed to have only the magnitude. So that's the difference that we have, or the difference that we can note between the two. So that's what we have, guys. So we shall quickly rush to 1.2, where we are given that there is a lorry which accelerates from rest. Take note, it accelerated from rest in 25 seconds and travels in a westerly direction from point S to T. All right, so we have got 2 conditions that we are given here. I want us to take note, guys. We have got 2 conditions that we have from S to T. All right, from S to T. That is the first part that we have. From this part that we have from S to T, it started from rest, and I told you guys from rest, which means your initial velocity is 0 to 2 meters per square second in 25 seconds. So also take note, guys, of the information how you are given. Please take note, because when you are given 2, it means you are supposed to get like your final velocity, but here they are not giving us final velocity, they are given the acceleration. But how the statement is written now is something else. You accelerate at a certain acceleration that you have to a certain velocity. Anyways, let's just take the way that we are given. So you've got u, which is 0 meters per second. We've got acceleration of 2 meters per square second in this case, and it's going to take 25 seconds for this to happen, which means we are given the distance, or which is sorry, are given the time frame of 25 seconds, sorry, because we are given the time that is going to travel from S to T. All right, then the question is calculate the displacement from S to T. We just need the displacement from S to T. All right, so if you are to cross check from S to T, this is the information that we have, which means if we are to represent, maybe we just wanted to represent this part graphically, maybe you find it difficult to obtain the formulas. So I'm going to work with both things here. All right, our velocity in meters per second and our time here in seconds. So I'm going to work with 2 things actually here. The first, I want you to understand that these are the things that you can actually represent on your VT diagram, which is the velocity diagram, where we started from rest in this case and accelerated to a certain velocity that we do not know. In this case, we do not know this velocity, but we know that this happened within 25 seconds, and acceleration is what is 0 because we started at rest. So this happened in 25 seconds. You can write your 25 here. So you do not know this velocity, but you know the acceleration was 2 meters per square second. All right, anyways, that's what we have. So we know that actually to calculate displacement using this, you're going to work with the area under the graph. All right, which means I'll explain that one. So I just want you to know what is happening graphically and also by calculation. Okay, anyways, by calculation, using this information, we've got this formula: 2as is equivalent to v squared. We can't use that one. We can't use this. I just want us to see v squared plus u squared. So this one we can't have anything. This one is supposed to be a minus because you've subtracted the other side. Okay, we move on to another formula with s, which is equal to ut plus half at squared. Yes, we can play around on this one because we have got in this case u is there, as you can see, t is there, acceleration, so we can use this formula here. So that means our s, which is the displacement in this case, is going to be ut, that's 0 times 25 plus half at squared, which is our a is 2 and our t is 25 squared. So it's a matter of substituting properly into the formula. So this is going to give us 0 plus, as you can see, we are going to be left with 25 squared, which is 625. Is that so? 25 squared, guys, is going to be. All right, so that is what we have in this case. So it's going to give us 625. Yes, that is it, if I'm not mistaken here. So guys, also cross check with your calculator there, but that is what you're going to have as your displacement. So like I said, we can actually work with this, or we can work with from the graph here. From the graph, which means your displacement is going to be area under the graph, which means you need to know this velocity. So remember that your velocity when given acceleration, acceleration is equal to change in velocity over the change in what? Over the change in time. So actually we have got acceleration here, which is 2, this one that we are given. So acceleration is equal to 2. The change in velocity, we do not know that change in velocity, but we know the change in time because we took 25 seconds here. So we can find the change in velocity, which is 25 times 2, which is 50. So as we can see, our change in velocity is going to be 50 meters per second if we cross multiply. All right, which means here we are going to have 50 meters per second. That is what we have. So using our velocity graph, our displacement is going to be equal to the area under the graph, which is the area of what? Of a triangle, which is half base times the perpendicular height. So you've got half times the base, this becomes your base, which is 25 times the perpendicular height. See that height that you are forced to calculate, which is this 50. So now you can use it, you multiply by 50. So using your calculator, still you must obtain the same thing, which is 625. So anyways, guys, that one I'm just showing you to say there are so many ways that you can actually attempt such a typical question. All right, so let's move on to another part now. From T to S, what happened from T to S? From point T, it then travels at a constant velocity for 2 minutes towards U. All right, so they are saying from this point T. Okay, so I'm just going to name our points. This is S, this is T, like this. All right, so from point T we moved with a constant velocity, which means this one is going to maintain like this. That's a constant velocity. All right, up to a time frame, in fact the time frame that was taken in this case was 2 minutes. Take note, this time is in minutes and our time is supposed to be in seconds. So 2 minutes in seconds, that's 2 by 60, which is 120. So we have to add this 120 to 25. So if we add, this will give us sorry guys, this will give us 145 actually. All right, this is going to be 145. okay, plus that one. It's 145 seconds. All right, then we move on. So which means from this part the displacement is going to be what? Because this is our u here, this is where we have our u now, from t to u on a constant velocity. So which means from this we can simply calculate what? The area under the graph, because it's just a rectangle. So which means this one can be direct. Just calculate the area of the given shape, that is your total what? That will be your displacement in this case. So you're going to have this like okay, take note we are given from t to u. All right, so this is 1.22 from t to u. Okay, so our displacement, like I said, is going to be the area, which is the length times the breadth. So it's going to be length times breadth, which is, remember here we have got 120 seconds in between here, because 145 minus 25 in between here we've got 120. So it's 120 times 50. This is the height. So we've got 120 by 50 in this case, which is going to give us 6,000. Yeah, that's 6,000 meters. So that's what we have, guys, in this case. Or maybe you wanted to apply that same formula. S is equivalent to ut plus half at squared. Still you can have the same thing, but what you need to note is that from t to u, this is your initial velocity here, which is 50. You started at 50, and which means your final is still the same, which is 50. So your u in this case is going to be equivalent to 50. The time frame is 120 seconds. Remember, from this part we are given time, which is 120 seconds. The acceleration now is equal to 0. It's no longer 2, because we are talking of t to u, and we know that whenever you are having constant velocity like this, which means your acceleration is equal to 0. So which means our acceleration in this case is 0. So using this formula, our s is going to be ut, which is u times t, that is 50 times 120 plus half at squared, which is half times a, which is 0 in this case, times t squared, which is 120 squared. So as we can see, guys, this is going to give us a 0 here, which means you're just left with 50 times 120, which is going to give you 6,000 meters. So still you could have used your formulas, or you could have just used your graph using the area. All right, so that's what we had. Then let's move on to another part, which is when we are at point u here, and then it starts to break and stops at point v, which means there is a deceleration in this case, because the brakes were being applied, or it's a retardation that is applying. So which means at the end we shall have our diagram like this, when the final velocity is at 0, like that. This is our point what? V, where we know that our final velocity is at 0, but we do not know the time. Okay, we are given that, which is 100 meters from u, point u. So which means in between u and v we have got 100 meters. So which means we are already given our s as 100 meters here. All right, so the question now is to calculate on 1.2 to the total distance traveled, which is 1 mile, because you are just adding, because you're now saying, remember you calculated the distance here, the distance here, so you're just adding all these. So let's just say this is our a, this is our b, this is our c. So you add everything together, because you calculated these ones before. This one you are given, so therefore this one is just going to be the first one. Remember we obtained on this one, that was half of this one, we obtained 625. So it's going to be 625 plus here, remember we obtained, it was 6,000 if I'm not mistaken. That is what we obtained, 6,000 meters here. And the last one we are given as 100. So we just add together this one. So this will give you 6,725 meters. So that is your total distance. Then the time taken for the journey. Okay, so what is the time? When we are referring to the time, because here take note, we do not have the value of t here because we are just given the conditions, but the value of t here is not given. So how now are we going to calculate the value of the time that was taken? So there are so many ways that you can actually choose to do. All right, we actually know that from u to v here we are given the distance. All right, the distance is there, and we do not know, what we do not know here is the acceleration, and we also do not know the time that was taken, but we know that the initial velocity from u to v is this one, the velocity at what, at 50 meters per second. All right, so this is what we are going to do. All right, this is what we are going to do. Let's take down our information. It can help us a lot. From u to v, we said our initial velocity is this one, which corresponds with what, with 50 here. So we've got 50 meters per second. Then our final velocity, this is now at rest, which means final velocity is at what, at 0. So our final is at 0 meters per second. We are given the only thing, which is our displacement of 100 meters. That is the only thing that we have for now, and we want to calculate the time. So guys, which means I have to find a formula which is going to suit all these three in order for me to have the time. And amongst the formulas that we have, guys, we are going to see that this is going to be difficult for us to see the formulas. Okay, anyways, this is your formula sheet, guys. As you can see here, we've got these formulas. But since we want to calculate the time, maybe we can play around one of the formulas, maybe this formula here. Okay, we can play around with this formula, because this one, yes, we can do, but take note, it's going to form a quadratic equation, and we do not have also the acceleration. We do not have this one. So we can play around with this to calculate our acceleration. Then, since we want the time, we can now play around with this formula to find our time. So let's play around with the first formula so that we can see, because acceleration is not there. So we are going to find acceleration first. From 2as is equal to v squared minus u squared. Take note, guys, how you the formula is given. Then we can make acceleration to be the subject, divide by 2s by 2s. So this is going to cancel. So your a squared is equal to v squared minus u squared over 2s. So take note, guys, it's stage by stage when you are given such type of equation now. All right, so our a is going to be v. Let's take our v, which is 0 minus 50 there. So it's 0 minus 50 squared over 2 times s, which is our displacement of 200. So we have to apply our calculators properly there. We are going to obtain an acceleration of minus 12.5 meters per square second. So we have the acceleration now, which is minus 12.5 meters per square second. So therefore we can find our t. Remember, there's a formula that I showed you, which is v is equal to u plus at. So let us make t to be the subject here, because we want to calculate the value of t in between that time frame between u and what, u and v. So it's going to be v minus u is equal to at. So you divide by a both sides, which means you're going to be left with t, because here you're going to divide by a. All right, so that means t is equal to v, which is our v there is 0 minus u. We said our u is 50 over a. So we now have the acceleration of minus 12.5. So definitely we shall have our time in seconds, which gave me 4 here seconds. All right, so this is not the answer that we are supposed to write. No, let us go back to the information and answer the question. Where is our question? Okay, here. Let's go back to the question and answer the question. The question is saying we must calculate the total time for the journey. The total time. The only thing that we did now is to calculate the time that is between these points. Okay, let me show here. Between these 2 points here on the last segment. Remember, this was your last segment from U to V. So we just calculated the time in between here and we said we have got 4 seconds. So which means the total time is going to be 145 plus this distance of what? Of 4 seconds. All right. So that is now your total time. So we are going to add these two, this time of 145 seconds. So which means total time is going to be 145 seconds where we are at this point plus the time that we obtained from U to V, which is 4 seconds. So you add that 4 seconds, which is going to give us 149 seconds. So that was our total time actually. So anyways guys, that's how they ask these questions. So let's see another question that we are given here. We are given that there is a lorry of 5 tons which travels at 90 kilometers per hour and switches off its engine when reaching an incline of 10 degrees. Calculate how far the lorry will travel up the incline if the friction is not considered. So take note here, the friction is not considered. So therefore, what is going to be the distance that was traveled? All right. This is it, guys. Let us just take our information because here we have got a lot of things that we have to consider here. This is a lorry with a mass of 5 tons, so which means we have to convert this to kgs. And in a ton, we have got 1 kg, so which means 5 ton we have to multiply by 1000, which is 5000 kilograms. The velocity in kilometers per hour, which means supposed to be in meters per second. So 90 divided by 3,6, which is going to give us meters per second of what? Of 25. All right, so you divide by 3,6, which is going to be velocity. We can just write it as U or even V. I don't know the way that you want to write it, but this is your initial velocity because it was traveling at that. Okay, anyways, it's fine. It switches off its engine when reaching an incline of what? Of 10 degrees. So there's an incline that it is reaching of 10 degrees. So it's like it's going down. All right, then now calculate how far the lorry will travel up the incline if the friction is not considered. All right, how it will travel up. Okay, this one is actually going up, but they are saying the friction is not considered. Guys, we've got a lot of things that we need here because we've got something like this. Okay, this is the load that is going up the incline, got a mass or whatever. So this is what you want to calculate here. Let's just call this our S. All right, the only thing that we have in this case is the mass and the velocity when it is traveling from this point to this point, to say is 25 meters per second. That is the only thing that we have. All right, now the question is, how now are we going to find this S, that is the distance that was traveled, guys? All right, let's take into consideration to say that let's say we know this side. All right, because we know this is our height, this one. Let's say we know this side here, this height. Definitely we can play around because we know that sine theta is equivalent to opposite over what? Hypotenuse, which is opposite, that's h, over the hypotenuse, which is s. So by simply finding h, we can find s because you can play around this your S is sine theta. If you cross multiply here, it's going to give you H. Then you can divide by S, which means S is equal to H over sine theta. So which means we need H, but where can we find this H? All right, there are two things that we know when we've got a body, or it's a lorry, it's a car, whatever that is moving. When this is moving, it is going to move until it comes to rest. So from that concept, we know that the kinetic energy and the potential energy at the end, they'll be equal. So these two, if they are equal, the kinetic energy and the potential energy, remember EP top is equal to EK at the bottom. That is after traveling, which is the same as the kinetic energy that is at the top is equivalent to the potential energy at the bottom. So that concept alone can be applied, because here in this potential energy, there is what? There is G, there is H. H is there, because we know that kinetic energy actually is equivalent to what? Of mv squared, and potential energy is equivalent to mgh. So we want this H here, so definitely we can divide by mg, because this is what we want. Divide by mg. All right, let's divide by mg because we want H here. This is the one that we want, so we're going to divide these two. So definitely H is going to be left with m, and m is going to cancel, so we are going to be left with half v squared over g. Okay, half v squared over g, and we have got this here, everything is there, so which means it is going to be half times v squared, which is your velocity in this case, which is 25 squared over g, which is 9,8. Yes, our H now is there, guys, because g is there, is 9,8. So we can play around this formula, and this is going to give us actually something like 31,887,755, which is going to end up as 888 meters. All right, so this is your H. Take note, guys, this is our H, which is 31,888 meters. But as we want to calculate what? S, by using this H into this formula. So we have to go back now and apply this formula that we transposed from. So now, guys, some of these questions you have to think along the lines, guys, because it's not like direct, like as we know. So that is our H, guys. We substitute 31,888 31,888 over sine theta, which is the angle. Remember, we are neglecting all the losses or the friction which happened, so this one is just going to be direct like that. So from our calculator, we're going to obtain something like 183,63567. So it's going to change to 636 because it was 63 something. So that is your S. So guys, as you can see, actually this question, it had a lot of things to consider, and I don't know if you can have any other option, guys. Let me know on the comment section so that we can see how we can attempt these typical questions. And also the issue of mark allocation, guys, what do you think about it? 4 marks for that? I don't know what you think, so let's talk so that we can see. But that's what we had on this question, so that we can have actually 16 marks. And we move on to question 2, which is on moments. So this was first question on 2.1. What is meant by a shear force? So actually this they can ask you guys at this question. So you can describe a shear force as it is a force that is pushing one part of a body in one direction and another part of a body in another direction. That is your shear force. Or someone can actually describe this as maybe in fact, there are so many ways, guys, to describe this. The algebraic sum of all the forces on a particular side of a section. Yeah, that can be a shear force. So anyways, that's what we had. On 2.2 we are given a question which is showing a light horizontal beam with A, B, C up to E of uniform cross section. So as you can see guys, here we have got a distributed load in between these 2 meters for 3 kilonewton per meter, 4 kilonewton per meter in between these 4 meters. So definitely we shall end up like this. We shall end up like this. 4 kilonewton per meter times 4 meters, that is 4 times 4, which is 16 here. So we shall end up with 16 kilonewton, which is now given in between the distance of what? If we divide this 4 by 2, is going to be 2 meters. 2 meters. I'm just saying, like, what you're supposed to visualize. This is what you're supposed to visualize. All right. Here between A and B, you do the same. You've got 3 times 2, which is going to give you 6 kilonewton. In between now, this is going to be 1 meter. 1 meter. So you have 1 meter here, 1 meter on that part. So that is what you're supposed to like visualize, because these are distributed loads. Anyways, we do not have anything on the other side. So the first question that we are given, before we talk of that, so this is actually what I'm saying it's supposed to look like, guys, to say that remember we've got 2 meters in between, so we separated 1 meter, 1 meter, and it was 3 kilonewton per meter. So you have to multiply 3 times 2, which is now 6. The same thing, 4 times 4, which is 16 kilonewton, but now given between 2 meters in between this distance of 4. So you divide by 2, which is 2 and 2. So just an idea of that is supposed to help you. Okay, anyways, the first question is to calculate on 2.1 the reaction of the supports B and D, which is this B here and this D. So sometimes they might not even tell you that the reactions are B and D, so you must know that the support are the ones which are facing upwards. All right, so definitely let's go back to our moments, guys. So I'm going to use this diagram here that I have redrawn. So we're going to take our moments first. Let's take our moments about B. So this is 2.21, so I'm going to take moments about B. So taking moments about B in this case. All right, so which means according to B in this case, if we are to cross check here how this is going to happen, we are referring to this is our B, and D is moving this way back to B. Take note the direction, guys. D going to D, that is anti-clockwise. So which means that's your sum of anti-clockwise moments must be equal to the sum of the clockwise moments. So that's gonna be D back to B here, which is a distance of what? 3 plus 4, which is 7. So it's going to be D times 7, or just 7D, guys. All right. Do we still have anything from this B that is moving in this direction of anti-clockwise? Okay, we still have this here. If we move on to the left side of B, remember the distributed load that we separated it now 6. As you can cross check, guys, this is moving this way, which is still in the anti-clockwise. Also, we've got this point load here of 20 kilonewton, which is moving also this way, which is anti-clockwise. All these, they are moving this direction, which is clockwise. So we are going to add these two on the anti-clockwise, which is 6 back to B here, which is 6 times 1. So it's going to be 6 times 1 plus 20 here back to B. We are coming back to B, so it's 20 back to B, which is 2 meters in between, so it's 20 times 2. All right, so we're gonna add 20 times 2. So we are done with the ones which are on the anti-clockwise. Then we move to these ones which are going this way, which is clockwise. So we have got 16 back to B here. So as you can see, now it's separated between 2 meters. Yes, now separated between these 2 meters. 16 back to B is 2 meters. So it's going to be 16 by 2. All right, plus you move on to this one. It's going to be 10 times 4. There's a distance of 4, so it's 10 times 4. Plus we move on to this one, which is 25. What is the distance between? This is 1, 3 and 4, so it's going to be 4 plus 4, which is 8, so it's 25 times 8. All right, so guys, you have to combine everything here. So this is going to give you 6 plus 40, which is 46. All right, so you're going to have 46, which is, you combine also this side, which is going to give us 272. So definitely you have to transpose. It's a positive here, so if you transpose to this side, it's going to be a negative 46. So 70 is equivalent to 272 minus 46, which is going to give us 226. So how can we find D, guys? This is now your mathematics here. So play around your mathematics. You are going to obtain your D is 32,2857, which is going to give us 286 kilonewton. Is it kilonewton, guys? Let's cross check. Yes, we have our other units in kilonewton, so this one is going to be our D, which is in kilonewton. So this is our D here, which is, I'm going to just write it here. So this one, we obtained this as 32,286. So we are going to use this later on. So let me just put it this way. So we have our D, so we can work with other part now, which is working with moments about that D now, so that we can find our B. So we are going to work now with moments about what? About D. So as you can see now, D, guys, we said from this B going to D is now opposing, which is clockwise. So this one is a straight clockwise direction. So you're going to work with the sum of the clockwise moments being equal to the sum of the anti-clockwise moments. So we have got B back to D, which is 7 meters. So we've got 7B. But do we still have anything that is on the clockwise? Okay, check note. Check here. This is your D. All right. There is a force here of 25 kilonewton, which is moving this way, which is clockwise. So it's still in the clockwise, I mean. So we have to add this, which is 25 times, there's a distance of 1 meter here. So it's 25 plus 1. All right, which is equal to all these, they are moving in the clockwise. If we have to cross check from D here, this one is clockwise, anti-clockwise, this is anti-clockwise, 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 all of these. So we have to add all of this back to D. So the first one is 10 times 3. There's a distance of 3 meters here, so it's 10 times 3. So it's going to be 10 times 3 plus, okay, we move on. We are done with back to D with 10. We move on to 16. So 16 here, back to, remember it's now 16 because of that distributed that we had. So this one is gonna be 16 times. But what is the distance now? This is 1 meter and this is 2 meters. So it's gonna be 2 plus 3, which is 5. All right, so we've got 16 times 5. Plus we move on, we are done with this 16 and back to 5. So if you are using this as a distributed load, it's going to be 4 kilonewton per meter times 4 meters times 2, so that it can make sense. All right, we move on to this one. It's 6 here, but what is the distance back to D? So as you can, we have got 3 plus 4, which is 7 plus 1, so it's 6 times 7, but 6 plus 1 is 7. 6 times 7. What else do we have back to D here? The last one here, 20. As we can see here, we have got 7 here plus 2, which is 9. So it's 20 times 9. You just add everything here. So it's 20 times 9. So guys, that's what we had. So we just have to combine 7B. In this case, this one is just going to give us 25. You combine everything here, which is going to give us 338. So 7B is equivalent to 25 to this side, which is going to be negative 25, which is equal to 318. Yeah. So In fact, there are so many ways that you can separate, especially for that distributed load, but because of time, guys, okay, let me just finish this one. Okay, so our B in this case is going to be 44,714,285. So this is 14285, which is just going to be 14 in kilonewton. So that's our B. So we can just maybe write this. This was 2,86. There was a 6 here, and this is suppose this man must give us a whole number here, because I'm now surprised there's 4 here. 714 kilonewton, like that. So this one, there was a 6 here, remember, guys. All right, so that is what we just had, guys. We worked our moments about D so that we can calculate B. So that's it. So let's move on to another question, see what we are given, which is to draw now the shear force diagram using a suitable scale. The diagram must be fully labeled. So guys, because of the paper that I'm using here, I cannot have any suitable scale that I can have here. All right, so it must, this type of equation is supposed to have a good graphical presentation that you're going to have, but in this case, guys, we do not have that. So what are you going to do now? We are just going to use what we have and present in a way that we can. All right, so let me just try and adjust. I'm supposed to go this way. All right, so it's going to be like this. All right, so let's see what you're going to have, guys. All right, so let's see, guys. I don't know how I made this setup today, but anyways, let's see if it is going to be clear. So as we know, guys, on the shear force diagram that we have to represent from where we started, actually from the point A moving to all these A, B, C, D, and E. All right, so here at A, if you are to cross check, we must be at 0, but there is a point load which is going down, which is of minus 20, because it's going downwards. So we're going to subtract 20, but we know that we are supposed to start at 0 here, which is at 0. But because we are having a point load, so we subtract that from 0. So 0 minus 20, guys, is going to give us what? That is minus 20. All right, so it is going up to minus 20, which is a negative, and you know that a point load you represent with what? With a vertical line. So this one is just going to up to minus 20 kilonewton. Okay, so in between that, guys, if we are to cross check, there is a distributed load in between these 2 points before we reach the support. So we are going to subtract 6 kilonewton, which is a distributed load. Remember how it's supposed to be represented, but it's a negative, this one. So we are going to subtract 6. Where are we subtracting 6? Where we are now at minus 26. So minus 20 minus 6, which is now minus 26. All right, so this is going down up to negative 26. Remember, this is a distributed load, so it's supposed to represent it like this. All right, so that is at minus 26 kilonewton there. We are now at point A, where we are given that at point A there, not at point A, at point B, where we have got a support, and we know that every support is a positive, and this support, we know that its value is 44 here that we obtained. So we're going to add 44. Where are we adding 44? Where we are now at this point of minus 26, we are going to add 44. So minus 26 plus 44, 714. This is going to give us something like 18,714 kilonewton, which means this one is a positive, so it is going up to 18,714. all right, so this is going up to 18,714. So it's just an assumption, guys. Let's just say it's here. This is just an assumption. We're just saying, assuming it's here. This is we said 18,714. This is where we are now at 18,714. 18,714 kilonewton, like that. All right, sorry. Now because of this presentation, now it keeps on doing like this, guys. I don't know, but anyways, between B and C there's a distributed load again, so we have to subtract 16 from where we are now at this point. Remember, we are at 18,714 now, so we subtract 16 and this will give us something like 2 comma something. So that is what you're going to have. 2 comma, this is going to be 2,714. So this is where we are now at 2 comma, just like what we're doing, guys. We subtract, do this and that, then we move on. There's a point load after the distributed load of 10 kilonewton, so which means we have to subtract again 10. So at this point direct we subtract 10, so 2,714 minus 10 is going to give us something like -7. But this is in between this, because like it can't be below this line, so it can be maybe somewhere here, right, where we have got -7 comma 286. So this is gonna give us 286 in kilonewton. So remember, we are at this point 10. From 10, which is at point C, there's a distance of 3 meters. Take note, there's no distributed here, so you are going to move a horizontal line because there's a distance in between. So you move a horizontal line in a horizontal line, which means you are still at the same point at -7,86. Then there is a support of 32 comma, so you're going to add -7 comma 286 -7,286 plus this support, because a support goes upwards and it's a positive, so you add 32,286. so if you add these, you're going to obtain 25. All right, so which means this is going upwards up to 25. So 25 is above 18, so it is going upwards, maybe somewhere here. Draw a vertical line here. I'm just indicating, guys, but I'm holding the ruler and I wonder why am I using my hands. I'm holding everything here. Okay, anyway, it's supposed to be direct somewhere here. All right, so this is now at what? At 25. This is where we are now at 25, just slightly above this 18. All right, because 25 is bigger than 18 and it's in the positive. Then from the point D, as we can note, from D to E there's a distance of 1 meter from D to E, so you have to maintain a certain distance. Let's just say this is our 1 meter, so which means we are still at what? We are still at 25 at this point. After at point T we have got a point load, which we know that it carries a negative because it's going down, so we're going to subtract 25. Where are we subtracting 25? Where we are now at 25, we subtract 25, which means we are going back to 0 kilonewton. Okay, so this is going down up to 0 kilonewton at this point. So that's what we are going to have as your shear force diagram, which is on 1 or 2 point. This is not 1 point, but this is a 2.22. all right, very sorry guys for this setup that I'm having. Actually, that's how these things they affect, but anyways, that's what we had in this case from the lesson on moments. So that is actually 4 marks and everything there, a total of 11 marks. So question 2, I think that's it. So move on to question 3, where we are given in this case to explain what is meant by the resultant of a number of forces. If you're working with a number of forces, what can you give as the resultant? So you know that the resultant is that sum that you are going to have represented with a single force. So all the forces, the sum of them represented by a single force, then that is what is going to be the resultant of a number of forces. So these ones, guys, please make sure that you memorize, read them, so that you understand what is happening there. All right, on number 3.2 we are given forces which are represented, then the question is to calculate or to have the sum of the horizontal components and the direction. So this one, in this case, is a clear diagram. I don't think we can do much adjustments. The only thing that we need to know, remember, are the angles with the horizontal. So here there's an angle of 45 degrees, which is fine. But what about this one? We do not know the angle in the horizontal between the force and the horizontal line. So we just need to continue with this line. So you can just maybe indicate with a broken line if you want. Okay, where we know this is going to give us what, 90 degrees to make it a straight line. So this will be 90 degrees, but we say the whole of this angle is 150. So this remaining angle, the one between the force and the horizontal line, is the one that we want to know, this one. So it's going to be 150 minus 90, because these two angles, they must give us 90 degrees. So that one is going to be 150 degrees minus 90, because we have removed this piece here. As you can see, we have removed 90 degrees. So what are we going to be left with? That is going to be 60 degrees. All right, so this angle here is 60 degrees between the force and the horizontal line, like just like this one, between the force and the horizontal line. That is how your angles are supposed to be. So that was the only adjustment that you just needed to do. Now let us calculate the sum of the horizontal and the direction, which is on 3.21. So you know that the horizontal components are the ones which use cos. So here we do not have anything. Okay, here we can take this is a straight vertical, so you're going to take this one, which is on the left side, and it's a negative. Remember, horizontal it's positive here, negative there, so it's going to be negative 40. All right, in between here, in between this angle of 45, we've got a horizontal which is 30 cos 45. Going back to the horizontal, it's going to be 30 cos 45, but carrying a negative, so it's going to be minus 30 cos 45. Okay, we move on to this side. We said this one is a positive, so it's going to be 60 cos 60 going to the horizontal, so it's 60 cos 60, but it's a positive, this one. All right, so that's what you're going to have in this case. So working around, playing around with your calculator, you're going to obtain negative 31,215,2132. So it's going to be 2132, because that 2 cannot change in Newton. These values, they are in newtons, so it must remain also in Newton, just like any other value. But horizontal, guys, remember, it can be either this horizontal, either you're going to the east, which is a positive, and negative to the west, and this is a negative, which means you are going to the west. All right, 3.212 in this case, we've got the vertical component in this case, which is going to be the ones that use sine. So already remember, this is our straight vertical component, so you're just going to take that one direct as it is, which is 50. All right, and also for vertical, you know that on top it's positive, below it's negative. Below this line, as long anything it's below this line, it carries a negative in the vertical, and this one cannot be a vertical component, guys. That one, it's a straight horizontal, so it's totally out. So you're going to have 30 sine 45, but with a negative because it's below the line, so it's going to be minus 30 sine 45. All right, minus 30 sine 45 degrees. Then we've got 60 here, which is minus 60. It's below the line, so it's minus 60 sine 60. All right, just like that, guys. We have to play around with your calculator as usual. So this is going to give us negative 23,174. Yeah, 572. So it's going to affect definitely our answer, which is going to be 175 in Newton, and it's a negative again. So vertical, remember, positive, negative, which is negative, is in the south, so the direction here is in the south. So that's it, guys. Remember, the question was not just to have the component, but to have the component and direction. All right, then after that, the magnitude of the result. They just say the magnitude there is no direction there, so we just need to find the magnitude, guys. Answer the question. So we know that the magnitude is equivalent to the, this is 3.23, which is r, is equivalent to the square root of the horizontal component squared plus vertical component squared. So we've got the square root of our horizontal component, this value, minus 31,213. So you can even not write the negative. It's not even an effect, because when you square negative, it becomes what? A positive. Your vertical component here, which is negative 23,175 squared. So that's it, guys. You place around your values in your calculator, which is going to give you 38,8758, which is going to be 876 if you round off properly. So guys, this just wanted the resultant, so we have the resultant there. So that's it. I don't know if you have any way, or the way that you see, let me know, guys, so that we can actually work on it in our next classes, so that we know what you think about this. Okay, on question 4 we are given what is meant by the angle of friction, and having this, where the angle of friction is the angle between the resultant force and the normal force. That is our angle of friction. Then we are given on 4.2 that there is a body of mass 80 kgs which is placed on an incline of 30 degrees with the horizontal. The coefficient of friction is 0.4. Then there is a force P making an angle of 60 degrees with the plane, which is required to pull the body. Take note, guys, how you attempt this question here, which states that it is required to. That is where you are supposed to obtain your answer. Is it pulling up the is it pulling it up the incline, or up the plane, or down, or is it pushing it up the incline? These are ways which makes the diagram to be different. To pull, to push, those are very, very important to note. Okay, so this time we are pulling up. This is pulled up the incline. So our diagram is going to be like this. All right, this is how our diagram is going to look like. Take note, we have got the normal body here. This is 4.2. Let's just have a diagram for 4.2, because it's very, very important that you have this. So we had a normal body here, which was like this. This is our normal body here, with an angle of what? With an angle here of 30 degrees. This 80 kgs with 30 degrees. So this is your 80 kgs here with 30 degrees. That is what we had on a normal body, with its coefficient of friction normally as 0.4, the one that we are given. But now there's a force P which is going to make an angle. This one, there's an angle between that force, and it is pulling up. When it is pulling up, this is it. This is your body. When you pull up, which means you are taking this upwards, this direction, that is to pull it up. To pull down, you are taking it down here. To push it up, which means your force is like this. It's pushing this. That is to push it to go up. But this one, it's pulling it up. So which means you are going to pull it going this way. That is to pull. All right. So we are going to pull this this way, guys, up the incline, which means there's a force. Since there's an angle of 60 degrees, which means our force is not direct like that. That is why I'm representing that like this. So this is our force P, which is pulling. So we can't say it's pulling, then this force is facing this direction. No, it will be pushing it down now. When it is facing this, it's now pushing this object down. But we want something that is pulling up. All right. So there's an angle in between like this of 60 degrees. Remember, we are given 60 degrees here. So definitely we are going to have the components according to the force P, which is this component here, which is according to your Pythagoras theorem, your solving triangles, your trig ratios. You can find this by P. It's an opposite to this one, so it's going to be P sine 60 degrees. This one is adjacent, which is going to be P cos 60 degrees. So that is what you're going to have on this. And take note also the direction. This is going this direction here because we are pulling it up. It is going up, and definitely your normal reaction. Anyways, so if you are pulling it up, what does it mean? There's definitely going to be that force that always opposes what you are doing. Always that opposes what you are doing, which is the frictional force in this case. All right, so definitely that is how it is going to look like. And we know this one, guys, we are going to even represent it in a easier and nicer way like this, so that we can understand what's happening, where we are going to have our angle of 30 degrees here, like this, and we have got our perpendicular component due to what, to this mass, which is the weight component, which is going to be perpendicular. That's F perpendicular or FC, depending with how you want to write it. All right, so it's going to be mg cos theta, which is cos 20 degrees, so 30 degrees. So here I'm going to write even theta, no matter the way that I want. Your parallel component, which is mg sine theta here. So actually these you need to know the diagram, the presentation of the diagram. You need to know what you are working with, not just to attempt a question not knowing the type of the diagram that you're going to have at the end. Everything will be distorted. This is what you're going to have at the end. Okay, anyways, let's try and attempt the questions now, which is the first question, which is the component P parallel to the plane. So which one? The component P, we are back to here. Remember, these are the components of P. Which one is parallel to our plane? This one is the one that is parallel. Parallel. So it's going to be P cos 60 degrees. So this is 4.21, which is P cos 60 degrees. But P cos 60 degrees can be simplified if you want, which is going to give you 0.5p. That is, if you want, you can write it as 0.5p. All right. We move. This is 4.21, guys. 4.22 now. All right. So let's see our 4.22, which is to calculate the gravity component parallel to the plane. This is now due to the gravity, which is due to the object where it is of mass. So this one, it's parallel to the plane, which means you're working with Fs due to the gravity here. So which means that's your Fs, which we said it's mg sine theta from W sine theta. Remember, W is equivalent to mg, so it's going to be mass of 80 times g, which is 9.8 times theta, which is 30 degrees. So you just need to put this note from here to here with the mass of 80. So that's 80 times 9.8 times sine theta, which we said is 30 degrees. This angle, not here. This one is for P. We are talking of this mass of 80 kgs. It's affected on this one of 30 degrees. So that's your parallel component, guys. So you have to just play around with your calculator, which is going to give you 392 Newton. So that's your Fs, which is 392 Newton. So that's it. That's it, guys. That's it. Let's see another part, which is to have the gravity component perpendicular this time to the plane. So which one is perpendicular to the plane? That's your FCs. This is your F perpendicular, F parallel. So you're going to work with FC, which is mg cos theta. So this is 4.23, which is FC. We said it's mg cos theta. So we are going to substitute, because this one is just a repetition, as it was 89.8 cos this one. So it's 80 by 9.8 by cos the angle, which is cos 30 degrees. Remember, the angle that you are working with is this one. So play around with your calculator. This is going to give us 678.939, something like that, which is going to 9639, which is going to be 964 Newton. Okay, this is direct newtons like that. So that's your FC. All right, then what do we have? So you got our FC, which is our perpendicular, then the magnitude of P. So guys, after this now, we have to find the magnitude of P. So anyways, the magnitude of P, guys, this is an unknown force, unknown value. That is why we have to determine its magnitude. But there is something that is very, very important, because there is a great relationship between this is 4.24, right? Where did I put this question paper now? That is 4.24. all right, 4.24. We know that we are given whenever you are given the coefficient of friction, you can actually work something from there, because is this the setup or what's happening, guys? I don't know, but that is what you're going to have, because you've got the coefficient of friction, which you know that is the frictional force over the normal reaction. All right, so if this be the case, therefore let us just find our frictional force in terms of P, which is the unknown force, and also the normal reaction in terms of P. So you can just find these aside. All right, so how can we find our normal reaction, our frictional force? So let's start with the frictional force. The frictional force, it's part of the horizontal components. That is, we are talking of forces to the left and the forces which goes to the right. So working with our horizontal components, we are going to see this. We know that F left, all the forces which are going to go to the left should be equal to the sum of the forces which are going to the right. So to the left in this case, which means you're working with horizontal, we have got these two forces here to the left. As you can see, guys, this is where you're considering a body at this point here. All right, this is where you're going. This is going to the left, this is going to the left. So these two, if we add them, they must give this one which is going to the right. As you can see, this is going up because it is the one that is pulling up. So we are going to add these two to the left, which is your frictional force plus your parallel component, which is Fs. It must give us F to the right, which is P cos 60, this one. So it's going to be P cos 60 degrees, the one that we obtained as 0.5 P, yeah, if we are not mistaken. Okay, anyways, we want this frictional force because it's the one that is on the formula. This one is not on the formula, so we need to make this to be the subject. So our frictional force is going to be P cos 60, which gave us 0.5. I still remember this one gave us 0.5 minus Fs. All right, and this one we have got it again. So your frictional force is going to be 0.5 P minus, you're not going to calculate this because you calculated this before, so you're just substituting your Fs here, which is 392. Even this one, as you can see, it's just substituting, so it's 392. So as we can see, this is our frictional force in terms of the unknown, which is P, in terms of the unknown, which is what? Which is P. So we need the normal reaction because it's part of our formula. As we saw here, guys, that there is a need for us to have the normal reaction. But where can we have this normal reaction? The normal reaction, if we are to look a closer, if we are to take a closer look on it, it's going up. So which means you're going to be working with forces which are going up versus the forces which are going down, which means you're working with vertical components in this case. So we are going to work with the forces which are going up being equal to the forces which are going down. So which force is going up? We're talking of the normal reaction, the P sine 60, this one, it's going up. Okay, these two, they are going up. So we've got our normal reaction plus P sine 60 degrees, which is equivalent to F down, those ones which are going downwards. We only have this the perpendicular component, which is your mg cos theta, which is your FC or your F perpendicular. So this will be equal to FC. So since we want to find this NR, the normal reaction, let us make it to be the subject of the formula. So it's going to be NR is equivalent to FC minus p sine 30. So it's going to be p sine 60 degrees, sorry, not 30 but 60. So our normal reaction is going to be, remember FC, we have got these values, we calculated them for, so it's just a matter of substituting what we obtained here when we calculated our FC, which is this value 678,964 minus sine 60p, and sine 60 is going to give us something like 0.866p. All right, so our normal reaction is there in terms of p, our frictional force is there in terms of p. So let us now come back and apply this concept here, because we now have this frictional force, the normal reaction in terms of p, and also the coefficient of friction, we have it as 0.4. We are given this, so it's now a matter of playing around with the formula. 0.4 is equivalent to the frictional force in terms of p, which is here, our frictional force here in terms of p, that's 0.5 p minus 392. Everything over the normal reaction in terms of what? In terms of p again, because remember that's what you want to calculate. So this is our normal reaction in terms of p, which is 678,964, all right, minus 0.866p. So you're just substituting your normal reaction. So these values, to say this one is a negative or it's a positive, you are not supposed to memorize that it's going to be positive or it's going to be negative. No, this one, it's created by the condition that you are working with. It is the one that creates both. That's why you see sometimes here it's a plus, or here it's a plus, or everything is a minus. That condition is created by the condition that you are given. So don't say I'm supposed to put a plus or a minus. No, it's, or to memorize, to just say when it's like, you work with the condition that you're given. Anyways, let's find our p. We can do this by cross multiplying and so forth. So this 0.4 is going to multiply everything here, so it's 0.4 times this value, which is going to give us 21, not 21 but 271,586. all right, then we multiply 0.4 and this one, which is going to give us a negative 0, this is 586. okay, so this is going to give us 0.3464, and this is p. all right, so it's going to be p in this case. Then if we are to cross multiply this side, as you can see, you're multiplying by 1, so it's 1 times 0.5p, which is 0.5p, 1 times minus this, which is minus 392. So it's now a matter of play around with your equations from your mathematics, guys. Transpose negative to this side, remember it's going to be a positive, so you're going to add this, and this is now positive. So if we add these two, you're going to obtain 663,5856, which is equivalent to, you transpose this negative to this side, which is going to be a positive, so it's going to be 0.5 plus this value here, which is going to give us 0.8464p. So we can actually divide by this value on both sides. So that's it, guys. We can have our value of p here by doing so. So p is going to be 784. So we're going to have 784,009,00945. So this 4 cannot change this 9, so it's just going to be like this in newtons. So p is the unknown force. So we are calculating the value of the force that is unknown, and also that if we substitute this force, therefore everything is going to give us the exact thing that we talked about. But because we have been rounding off these values, definitely one or two things will be affected, but the concept is that is what you're going to have there. All right, so that's how they actually ask these questions, guys. So you must be very, very careful the way the question is given or presented. And we move on to the question 4.3, where we're asked to state 3 disadvantages, or this one is advantages, sorry, of friction as applicable in engineering. So that's 3 marks, guys, to make a total of 14 marks. So these are the advantages that I am having, guys, of friction in 4.3. So there are so many ways actually that we can use to prevent slip between surface to contact surfaces, to remove the materials, to transmit movement by means of belts, to bring movement to stand still, to enable movement. So there are so many ways that we can work. Yes, we've got a lot of disadvantages also when it comes to friction, but still we have got advantages again. So I don't know, but you just need to work with to say how many or the number of advantages versus disadvantages is the one that is most important. Okay, give 2 advantages of steam. All right, this one is actually on steam. So remember, steam has got a way. Remember, I always say that when you're working with steam, always think of coal also and water, because this they work hand in hand. So steam can be used repeatedly. Coal and water are reasonably cheap and readily available. Then a steam installation is a long life. So despite the disadvantages of the cost of the initial cost and so forth, but in this case we've got some advantages that we can actually put into action or into consideration. Okay, on number 5 we are given that on 5.2, where we've got a fuel which has got a heat value. Take note, we are given the heat value of the fuel, which is 42 megajoules per kg, was used in an engine that develops 15 kilowatts. And if you have to cross-check this type of a question, we actually worked with this from previous questions. But anyways, we've got the heat value. So I'm just going to have this information down. Our heat value, remember, this is 42 megajoules per kg. All right, and the power, which is the output power, this one. So your heat value, that's 42 megajoules per kg. And we said also we've got the output power, which is in this case your 15 kilowatt. All right, so you've got 15 kilowatts, and we are given the time frame. The test lasted 45 minutes and the thermal efficiency was 45%. So take note, we have got the time which everything took, which was 45 minutes, and we have to convert this to seconds. So if you multiply by 60, guys, to seconds, it's going to give us 2700. So even we do not know we are going to have seconds or not, but let's just have it in seconds. And the thermal efficiency, which is 0.45, remember 45% as a decimal divided by this is going to be 0.45. That's your efficiency, or you can just work with it as a percentage like that. So if you use it as a decimal, then you don't use 100% on your calculation. If you use it like as a percentage, therefore you have to use 100% on your calculations. All right, so this is what I'm trying to say, like the year where they're asking us to calculate the equivalent power of the fuel. What was the equivalent? That is the input power to the fuel. All right, so of the fuel, I mean not to the fuel, but of the fuel. So from our efficiency, because we've got thermal efficiency there, so we can actually play around the thermal efficiency, because we know that thermal efficiency is equal to power output over power input times 100%. So like I said, if you work with a percentage, therefore you have to multiply by 100%, but in this case I'm going to use a decimal, so there's no need for me to multiply by 100%. I'm just going to substitute my efficiency in this case, which is an efficiency of 0.45 as a decimal. So already I have applied 100% because I divided, so I'm not going to use it. Take note. power output is 15 kilowatts, so it's going to be 15 kilowatts in this case over the power input. So we can play around this to find the power input. Definitely we have to cross multiply 0.45 times the power input is equal to equivalent 15 kilowatt. So divide by 0.45 by 0.45. All right, we shall have our input power, which is in kilowatts. Already this is in kilowatts. Okay, so 15 divided by 0.45 is going to give us 33,3333 and so on, which is 33 kilowatts. So that is your input power in this case, which is 33,333, like that. Okay, so let's see another question, guys, which is the heat energy dissipated by the fuel. Take note, we now have the power for the fuel. What about the heat energy now? There's a good relationship between power and energy, because we're talking of something that was sent by the fuel, and where we know that power is equivalent to energy over the time, and this time is supposed to be in seconds. So we have got the input power. All we need is to find the energy now, which is E. So you can play around this E, cross multiply. In this case, it's going to be 1 times E, which is E is equal to P times T, which is PT. But take note, since you are using your time in seconds, this power is supposed to be in watts, not kilowatts. And here we have got kilowatts. Here we have got kilowatts. So we are going to multiply. So it depends. If you use kilowatts, which means you must be very careful with your answer. Okay, so if you use 3,3, maybe you want to avoid this issue of converting, you use this. It is already in kilo, this one. All right, times the time in seconds, which we said our time in seconds. Here, this was our time in seconds, 2,700. All right, so if we multiply this, we are going to obtain 89,999,1. But take note, we said this is in a kilo. We used the kilo already, so which means these are going to be kilojoules. So this is your energy in kilojoules. But guys, take a closer look. We can convert this to megajoules, because if we divide by 10 to the exponent of 3, or if we divide by 1000 here, we are going to be left with 89,9991, which is now megajoules, because it will be like 10 to the exponent, suppose already there was a kilo here, so it will be 10 to the exponent of 6 joules, which is megajoules. And this can be rounded to 89,99, or you can have it as 90 joules, guys. This one, guys, just take a closer look. You can just write it as 90 megajoules here. All right, so that's our energy. Why do I need you to convert to megajoules? Remember, your heat value there was in megajoules per kg. So you never know, you might need to use this heat value, and you've got your answer in kilo. Yes, it's fine, but just try to have it in same units. I'm not saying different units you're going to obtain the wrong answer. No, I'm just saying try to write this in same units. Okay, anyways, that's what we had from this part. So what about the other question that we are given? So let's see the part now that we have, where we are asked to calculate the mass of the fuel. So as you can see now, we need to use that heat value, because there's no way that we can find the mass of the fuel. We have to go back to the relationship between the energy and the mass, where we know that the energy that we just determined now is equivalent to mass times heat value. So if it is equivalent to mass times heat value, therefore let us find the mass by dividing by heat value, which is our mass is going to be the energy over the heat value, which is the energy in this case. Remember now, you see where we have to use this So remember, we obtained 90 megajoules. This one, 90 megajoules. So it's going to be 90 megajoules over the heat value, of which our heat value is 42 megajoules per kg. So this is 42 megajoules per kg. So definitely our answer is going to be kg, because this will cancel. So we're going to be left with 1 per, like this. Per kg means 1 over a kg, like this. So 1 divided by 1 over is going to be a kg. So this will be our mass in kgs. So what are we going to obtain? We're going to obtain 2,14285, which is 3, because 285 is going to change this into 3. So this is the mass of the fuel, which is going to be 2,143 kgs. So that's it, guys. That's how they want you to play around these formulas. It's very, very important that you understand your formulas anyways. Then here we are given that the following data refers to an aluminium rod which is 200 centimeters in length. So we've got an aluminium rod which is 200 centimeters in length. So we can convert this to meters. Okay, let's just take our information here. Remember, you are working with, or you can just add it here, guys. We can just add it here. So this length of the aluminium, which is actually, it's like the original length, which is 2 meters. You have to divide by 100, which is 2 meters, or you just leave it. We do not know how we are going to apply it. Let's see the other part. We are given the initial temperature of the rod, which is your T1, that is your initial temperature. Then the amount of coal, which is the mass. So you're given the mass of 750 grams. So to kgs, you divide by 1000, which is going to give you 0.575 kgs. Yes. Then the percentage of heat transferred to the rod. There is a percentage of it which was transferred to the rod. All right, which is 60%. We shall talk about this. Then the mass of the rod is 10,000 grams. If you divide by 1000, which is going to give you 10 kgs, which is the mass of the aluminium rod. And definitely we are talking of aluminium, so we might need also to know the heat value of this aluminium and so forth. So we have to go here. Do we have that? We need the heat value, the linear coefficient. Maybe we can just have our linear coefficient. Okay, let's just leave this. We'll see according to the question that we are supposed to answer, but we might need the heat value. Okay, the heat value that we need is there is coal which is burnt here. Take note, guys, the amount of coal which was burnt. So we need that heat value of coal, exactly, which is 30 megajoules per kg, this one. So we need the heat value for coal. So this is our heat value for coal, which is 30 megajoules per kg, not for aluminium, but for this coal, which is the fuel. Okay, which is the fuel, yeah. On 5.31, we need the quantity of heat that is transferred to the rod. Okay, take note that they said 60% of heat transferred to the rod, which means we need to know the heat first of coal, then the one that was transferred to the rod, which is the aluminium rod. So what is the heat if you're talking of a fuel? So remember that heat of a fuel, you can write it as E coal, or you can write it as Q for coal, which is the fuel, is equivalent to the mass times heat value. So that's our E in this case, which is mass times heat value. So what is the mass of coal? Remember, the amount of coal which was spent is 0.75 kgs from that 750 grams. 0.75 times the heat value of coal, which is 30 megajoules per kg. 30 megajoules per kg. So this is kg. So definitely kg and kg will cancel. Your answer is going to be in megajoules only. So it's going to be 22.5 megajoules, because kg and kg will cancel. So that's your energy, guys. But they are saying there is a transfer of percent, which is 60%, which was transferred to the rod, and that is the one that we need, the one that was transferred, which is 60%. So we are going to find 60% of this, so which means our Q for the rod, which is the aluminium rod, is going to be 60% of this. And remember, 60% simply means 60 over 100, or 0.6 times 22.5 megajoules. All right, so play around, guys, your calculations here. You're going to obtain 18.5 megajoules in this case. Okay, so this is the heat that was transferred to the aluminium rod because of that 60%. Okay, then the final temperature of the rod, which is on 5.32. What is the final temperature of the rod? Where are we having this final temperature? Where is it taken from? Okay, remember we have got for this aluminium, we are given the initial temperature, the mass of it, and also we can have the specific heat capacity, because this is a metal, not what we wanted to calculate that previous part. So we need the specific heat capacity, which is going to be 900, because you're talking of the specific heat capacity of aluminium, which is 900 joules per kg degrees Celsius. 900 joules per kg degrees Celsius, like that. Okay, so we know that there is a relationship, because actually the heat that is for the aluminium, which is the rod, in this case Q rod, which is the aluminium rod, we obtained this as 13.5 megajoules. Remember, this is what we obtained, 13.5 megajoules here. And this is for the aluminium, which is the rod that you are given, which is not the fuel. So we are not talking of the heat of the fuel here. We are talking of what? Of the heat of the rod, which we know that Q is equivalent to mass times the specific heat capacity times the change in what? In temperature. So what we can do is to calculate the change in temperature. Okay, because the question wants us to find the final temperature, so we can calculate the change in temperature. Then we use it now to calculate the final temperature, because we know that T2 minus T1 is equal to what? To the change in temperature. So let's just substitute our values, guys. So Q for the rod, which is the 75%, this one which was transferred, which is 13.5 mega, means times 10 to the exponent of 6, that is mega, is equivalent to the mass of what? Of the rod, which is the mass of the rod is 10,000 grams, which we said is 10 kgs if you divide. So it's going to be 10 times the specific heat capacity of this aluminium rod, which is 900 joules, okay, times the change in temperature. Definitely we can divide this by 10 times 9 both sides, 10 times 900 both sides, 10 times 900, which is just 9,000 actually. So you can have your change in temperature, if you do this properly, which is going to give us 1500 degrees Celsius. Take note, this is not your answer. The question wants you to find the final temperature, and we said change in temperature is equal to T2 minus T1. So which means definitely your T2 is going to be the change in temperature, in this case, plus T1. All right, so we are going to add the change in temperature 1000. There was a change in temperature of 1500 degrees Celsius, plus the initial temperature, which is where we started from. Remember, our initial temperature was 25 degrees Celsius. That was our initial temperature here. So we are going to add, which is going to give us 1525. Okay, that's your T2 from that part. So actually some of these questions will be like boring to answer, but guys, you have to bear in mind that every part is a mark that it is going to play, whether you are losing it or you are gaining it. So every portion is a mark. Okay, anyways, we move on to the final length of the rod. The final length, this time we are working with the length. So let's go back to our relationship between the length and the change in length and the original length, where we know that is equivalent to original length times the specific times the linear coefficient of expansion. This time you're working with the linear coefficient of expansion times the change in temperature, of which the change in temperature is already there. We calculated this. So what we need is this linear coefficient of expansion of aluminium. So for the aluminium, the linear coefficient of expansion is 23 times 10 to the exponent of -5. That is what you are given on your formula sheet. All right, so which means our change in length is going to be the original length. Remember guys, the original length, when we listed our information here, we said this is an aluminum rod which is 200 centimeters, which we said is 2 meters. So you can work with this in meters or in centimeters, so depending with what you're going to have, but our original length in this case is 2 meters. All right, so you shall have this as 2 meters times, remember we said 23 times 10 to the exponent of -5 here, the linear coefficient of expansion, which is 23 times 10 to the exponent of -5 is 23. Yeah, 23 times 10 to the exponent of -5 times, instead of you now starting to calculate this change in temperature, guys, we already have this. Remember when you calculated our change in temperature, we said this was our change in temperature, which was 1500, if you still remember, or you just subtract T2 minus T1, you are going to obtain the same answer, which is 1500. If you do this properly, guys, you must obtain the same answer there. So this is what you're going to now have at the end, provided that you multiply it properly. Take note, guys, here we are not talking of T2, we are talking of the change in temperature. So the change in temperature is T2 minus T1. That is why you have to write this 1500. The change in temperature is the one that you write, not the final. This is going to give us 0.69, which is in meters. If we are to do this properly, guys, if we are to do this properly, then definitely our final length is going to be the original length plus the change in length, which is the original length was the one that we had, 2 meters, plus the change in length of 0.69, which is going to be 2.69 meters. So that's what you're going to have, depend with what you convert to millimeters or so forth, but in this case we can just have this in meters. So take note here, guys, what I'm saying here, you use the change in temperature, the change in temperature, which is T2 minus T1. You don't use this T2, no, you don't use that value. So please, I want you to correct all those errors and mistakes, because here the final temperature was your T2. It is not the one that you use. You now subtract T2 minus T1. Okay, so that's it. Then on question 6, which is actually on hydraulics, we are given on hydraulics that 6.1, write an equation for the suction head in terms of the delivery head and the static head. Guys, this equation, we talked about this a lot of times, where we said it's actually saying that the suction head is equivalent to, or let me just write it down here. So remember that your suction head is equivalent to the static head. So this is suction head is equivalent to the static head minus the delivery head. Okay, so this one is your static, so you have to write in full: static head, delivery head, suction head. But if you have to cross check the question parts that you have been doing on hydraulics, you'll see that this one we had, and I even showed you how where it is taken from the diagram. So make sure that you watch the videos on hydraulics so that you can be able to understand it. You're just like doing revisions. Okay, anyways, we are given the following data refers to a single stroke pump driven by a diesel engine which is to deliver water to a reservoir above the pump. The working pressure, the volume of water delivered per hour, which is 25 cubic meters per hour. And we are given also the output power of the diesel engine, which is 9.45 kilowatts. So the first equation is to calculate the maximum height of the reservoir above the pump. That is on 6.21. So where can we have the maximum height? All right, remember guys, we've got pressure. This is our working pressure here, which is the only part that can actually work with the height, because we know that pressure is equivalent to rho g, which is density times gravitational acceleration times the height. Yeah, so let's play around this formula, guys. 6.21. So since our pressure is equivalent to rho g h, so this is rho, which is density. So we want h, so you can divide by rho g, which is pressure, over density times your gravitational acceleration is going to be your pressure. So just try and put this kilo means times 10 to the exponent of 3. So it's going to be 345 times 10 to the exponent of 3, so that we obtain exact values over the density. We do not have this, but we are talking of what? Water. All right, so this is actually water. So we need the density of water, but now I think guys we are used the density of water is 1000, that one. Anyways, let's see where we are given this, the density of water. We have got 1000 kgs per cubic meter. So we've got 1000. All right, so this is going to give us, look where I'm writing now. So this is 1000 times 9.8, like that. Okay, so using or applying your calculator properly, you're going to obtain 35,20408, which is 204 millimeters. So this is will be our height. What about the work done by the pump? Take note, per minute. This one we've got volume per hour, because we know that work done is equivalent to pressure times volume, but here we need this per minute, so we shall convert because we know that in an hour we've got 60 minutes. Is that so? Okay, let me put this way. Let me put it this way. In an hour we've got 60 minutes, remember, so you're going to divide that volume to be volume per minute, because we said work done is equivalent to pressure times volume, but this one is going to be volume per minute. Since they want our work done per minute, so we shall use volume per minute. All right, but that's not what, like all the questions that are. This one is a question under instruction. We know that we are supposed to use volume per second, but this one is an instruction that you are given, so you answer according to the instruction that you are given. All right, so our work done is going to be the pressure, which is 345. So the moment I use this kilo, which means my answer is going to be in kilojoules. Okay, so it's going to be 345 kilo times the volume per minute. Here we are given the volume per hour, so divide by 60, which is 25 over 60. So this is now our volume per minute. So definitely if we multiply these two, our answer is going to be something like 143, okay, 75, 143 comma, because already I have used the kilos, so it's going to be comma 75. This is what I'm going to obtain, which is in kilojoules per minute. So take note, that's our work done per minute. Then the final, sorry guys, where we are going, look where we are going now. We are here. This is issue of working with the full paper. You see how it takes, guys. So the output power of the pump now, which is actually 2 marks for that. What is the output power? We've got the work done, which is, remember, work done is just same like energy, but this time you must use in seconds, because you need the actual power here. So remember, power, your time is supposed to be in seconds, so you have to convert this to second. All right, so that is what you're going to have. You have to convert to the time there, because you've got your work done All right, this is 6.23, which is power, which is energy over time, which is actually work done over the time taken. So remember, our work done was 143 comma something, so you have to multiply that by it's gonna be 143.75 times 10 to the exponent of 3, because that was kilo joules over the time. It's per hour. This was per hour. The time is already there. It's per hour, which is 3,600. Remember, 60 times 60. Okay, so it's gonna be 3,600 per hour time. But this is supposed to be per second. Power per second. That is why we have to do this conversion. All right, so playing around with your calculator, it's going to be 39.959305 and so on, which is going to be 39.931. Okay, so there's your power, and it's just measured in watts because we removed that kilo, so it's not going to be in kilowatts because already we removed it. So it's going to be 39.931, just like that. Then state the pascals, or state Pascal's principle in words. What do we have on Pascal? Okay, so this is what we have, guys. On Pascal, I'm going to say this diagram is going to be clear, but that's, I mean, the illustration. So it states that the pressure that is applied on an enclosed system, that pressure will be spread evenly through the enclosed liquid. So it can be a liquid or it can be a fluid actually, and the same throughout. That is what we have. So I think from your definitions and so forth, you can actually understand what's taking place there. So guys, that's what we had on question 6.3, which is actually 12 marks for that. Everything, I mean, on question 6, everything 12 marks there. So it's very, very important that you understand the concept of how to attempt these questions, guys. It's very, very important. All right, on number 7, which is 7.1, we're given to state Faraday's first law of electrolysis in words. So what do we have, guys? We know that and this one, guys, I think I don't know how many times if we listed this. So anyways, that's what we have, that if there is a mass of a given substance liberated at an electrode of a cell, it is directly proportional to the quantity of electricity passed through the cell. That is the quantity of electricity that is going to be in the cell. Okay, anyways, we are given on 7.2, where we are given a circuit consists, take note, guys, of 4 cells with the EMF of 1,5 each, which are connected in series, and each cell has an internal resistance of 0,5. Okay, so these are actually in series. So in series, you just have to add, therefore you add 1,5 4 times, or you just add 1,5 times 4, because we have got 4 cells in series. We just multiply by 4, which is going to give us 6 volts as our total voltage. The same thing on this 0,5, you multiply again by 4, which is going to give you something like 2 ohms. So that's your internal resistance, that's your total voltage of circuit. Okay, anyways, they are saying there are some things that we have which are connected to the battery: 2 resistors which are parallel, and a radio and a loudspeaker. All right, so this is like something like this, where we've got like everything combined together. Let's just say this is now a single battery. We've got the voltage and the internal resistance together here, which is our voltage. We said it's 6 volts, internal resistance 2 ohms. Okay, which is 2 ohms. Everything is now there. This is the total voltage, the total internal resistance. Then, since there are resistors which are in parallel, then also there is a radio and a loudspeaker. Let's just say this is our radio here. let's just put our radio here, because these ones they are in series, so you can just put it anywhere as long they are in series like this, but they are connected, or this connection is connected to a parallel circuit, which is this one. So we are going to have a parallel circuit here. So let's just say this is our radio here, so this is our radio here, this is our loudspeaker here. All right, so the two resistors which are in parallel are 3 and 6. These are the ones which are in parallel, 3 and 6. We've got 3 ohms, 6 ohms. Then definitely the radio we are given, the radio, it's 4 ohms. Loudspeaker, 2 ohms. So the loudspeaker here is 2 ohms. The radio is 4 ohms. All right. So that's how your circuit can be generally presented, like on that information that you are given. So now, in order for us to calculate the total resistance of the circuit, we can now analyze to say we have got internal resistance, we have got a radio, we have got a loudspeaker, we have got a parallel component in this case. So which means we shall have something like this as our total resistance. We shall add the total to the internal resistance, the radio, and the loudspeaker. So we have got the resistance of the radio, I don't know, we just write as R radio, I don't know, plus the resistance of the loudspeaker, plus the resistance for the parallel circuit, which is our R parallel like this, or you can just write it as RP. All right, where we know this one, if there are two like this, you can just use product over sum to obtain your answer, because they are just two resistors here, guys. All right, so your RT is going to be the internal resistance, that one for the two resistor, for this resistor that there were 4, yes, which gave us 2 ohms. So it's gonna be 2 plus the resistance for the radio, which is 4 ohms, plus of the loudspeaker, so it's 4 plus 2, plus the parallel circuit, which we said if there are 2, we can use product over sum, which is 3 by 6 over 3 plus 6. So it's going to be 3 by 6 over 3 plus 6. Product over sum, you're done. That's your parallel circuit. So you're going to add 2 plus 4 plus 2 plus, from this parallel circuit, we are going to obtain also 2. And if we add everything, that is going to give us 10 ohms. All right, so that's what we had, guys. This gave us 10 ohms. So let's move on to another part. Let's see another part here where we are given to calculate the current flow in the circuit. So definitely current is the total voltage over the total resistance in this case. All right, so this is 7.22. So the total current is going to be the total voltage over the total resistance. Remember, it's voltage over resistance. So we've got the total voltage. Remember, from those series, the voltages that we had, cells that we had, which is 6 volts in this case. So it's going to be 6 volts over the total resistance, the one that we just calculated now, which gave us 10 ohms, if you still remember here. So we just have to divide by 10, and that's going to give us 0.6 amps. So this is your total current, which is going to be 0.6 amps. Okay, anyways, let's see from this. Normally they want you to play around that current. They want you now to calculate the voltage drop across the loudspeaker. So what is then our voltage drop across the loudspeaker? Take note, this is your loudspeaker, and we know that current is the same, the current that is going to flow here, like the total current, because this one they will add up back here. So here we have our total current here, but in this, yes, they are going to be different in these two, but here and here we have got the same current. Even on this internal resistance, we've got the same current, actually, for these two, not for this one. Take note, so for these two. So which means, in order for us to have the voltage across this loudspeaker here, because it's the one that we need to calculate, we shall just calculate, multiply by the current, okay, because that's what we need. So the voltage across the loudspeaker, which is 7.23, that's voltage across the loudspeaker, is going to be current, which is the total current times the resistance across the loudspeaker there. So the total current, remember we obtained 0.6. Yeah, okay, this is it here. See, you're working with many papers, guys. You see confusion now. 0.6 anyways, multiply by the total resistance for the for that loudspeaker. And this loudspeaker is going to have a 2 ohm resistor in total, so it's going to be 1.2 if you multiply properly from your calculator, or even by sight you can see that the answer is direct. Anyways, that's it on 7.2. Then let's see on 7.3, where we are given that there is a single phase transformer which has to supply a voltage of 240 volts, which means you are given V1 as 240, which is primary, so let's just say P, and a primary current in this case, which is IP. You can write this as I1, I don't know how you want to write it, which is 6 amps at full load. The secondary current, which is IS, is gonna be 0.4 amps, and there are 600 turns on the primary. So on the primary here we've got the number of turns, which is 600 turns in this case. All right, so the question is to calculate the number of turns on the secondary. So remember, guys, it's a matter of joining of formulas. So you've got here, we do not have anything that is complete except for the current, but we know that the relationship between current and the other ratios, it interchanges. So if we start with IP, okay, let's just say NP, because one, you know, anyways, you can start with any, you can write IP over IS, then you interchange on the other hand. But here, if we can start with NP, you can understand me much better. We know that it's supposed to be NP over NS. Then the moment you write in terms of current, it interchanges. Remember, it's IS over IP. That will be what you're going to have. So it's just a matter of cross multiplication. You can substitute your values, cross multiply, because NP, you have it. Your NP here is 600. Remember, you're given 600 turns. So it's 600 turns over the secondary one, which is the one that you want to calculate, is equivalent to IS, which is the current on the secondary, which is 0.4, over the current in the primary. In the primary, we've got 6 amps. So let's just play around, cross multiply, which is going to be 6 times 600. In this case, is equal to 0.4 NS from your mathematics, guys. Then you can even divide by 0.4 by 0.4 here. So you've got your number of turns in the secondary side, which is going to give us 9,000 turns. So this is going to give us 9,000 turns. Actually, that is the number of turns that we had on the secondary. Anyways, let's move. So you can even write it here. Guys, now I'm disturbing this. Okay, NS, we got 9,000 turns. Anyways, what about the secondary voltage? So it depends with you. Remember, this NS, you're the one who calculated it. So if it is wrong and you use it to calculate the secondary voltage, which means your answer is going to be wrong. So to avoid that, you can go back to the same concept, but now working with voltage, because this one we do not trust this, because we are the ones who calculate. But yes, it's me, I will calculate, it's fine. But I'm saying, if it is you under exam condition, don't trust the answer that you calculate at that moment. Trust the values that are already given. Work with those values you're already given. So that's gonna be, now we want to calculate the voltage. So it's gonna be 7.32, which is now VP over VS. But remember, it changes when it comes to current, so it's IS over IP. So VP, we've got it on the primary, which is 240, over VS, the one that we want, which is the secondary voltage, is equal to IS over IP, which is IS over IP, 0.4 over 6, 0.4 over 6. So play around, cross multiply again, it's going to be 240 times 6 is equal to 0.4 VS, divide by 0.4, by 0.4. So that's going to be your Vs in this case. All right. So our secondary voltage will be, if you divide properly, this is going to be 3600 volts, guys, and it's a big value. All right, but that's what you're having, 3600 volts. And what about the secondary power? We have got the voltage and the current, so you can simply multiply positive voltage. We just determined it now, so which means our secondary power is going to be simply the voltage times current. Remember, VI, voltage times current. So the voltage, which is the one that we just calculated, which was 3600, times the current on the secondary, which is 0.4. So you just combine these two, which is going to give us 1440 watts. And this is power. Remember, this is a DC this is a DC machine, a DC gen, so that is why a DC part, that is why voltage times current is giving us what, 1400 in watts. If you, because remember, if you are working with an AC circuit, if you're having that, then you're going to work with volt, amperes. Actual power is the one that you measure in a kilowatt. So it depends with what you're working with in this case, but that's what you have, which is our power. But you can write even in kilowatts if you want. So it's gonna be 1,440 kilowatts, which is just same as 1,44, because you just divide by 1000 so that it can be in kilowatts. So that's it, guys. As you can see, this question had a lot of things. Actually, that's why we have got 16 marks, because here we've got a lot of things that we're having anyways. But if you are to cross check here, you will see that, yeah, that's how they actually ask these questions. It's only like how you are supposed to attempt or to answer the question that is important. Okay, anyways, let's see on question 8, which is on chemistry, where we are given on 8.1 to give the definition of an ion. So if you're given an ion, how can you best define that? So an ion is simply a charged atom. So I'm going to put this definition so that you can actually see. We are saying an ion is simply defined as what? As a charged atom. So we have on 8.2, where we are given to give examples of the alkali earth metals that we can work with. So there are so many alkali metals that we have, which is lithium, sodium, potassium, rubium, cesium, and so forth. So there are so many that we can consider, or that we can have in this case. Anyways, that's it. Then the other part there, we are given to complete the statements by choosing the correct option in brackets. So that's what you have. So here, zinc is actually smooth, harder, or softer than tin. So how can you compare zinc and tin? So actually zinc is harder than tin here. So here we're going to have harder tin, and in this case, but that tin that we're talking about is, but that same zinc, how is it compared to copper? Because you're comparing zinc with tin, the same zinc you're comparing with copper. So how do you compare? Is this one is actually softer. Zinc, remember, that is softer than copper. Then nitrogen is a colorless, odorless, and tasteless gas. Yes, we know that. And it forms how many percent of the volume in air? So remember, nitrogen, when it comes about the air, it carries 79% when you are referring to volume. That is what you're going to have in this case, where at that moment they can ask you about air, which is the oxygen at that moment, because you'll be sharing nitrogen and oxygen. So oxygen is going to carry 21%. So as you can see, nitrogen is the one that is going to have the highest percentage in terms of percentage, which is 79% in terms of volume. Also, they can ask you in terms of mass. So you must know all these differences in terms of mass, in terms of volume, and also the percentages for every part that you'll be given. So that's it, guys, that we had on question 8, which is 6 marks. and actually to mark this total of 100 on this question paper. So actually that's how they ask, or how they give these questions. So what you need is to work on much question papers and revision, preparing yourselves for the exams which are ahead of time, so that by that time you'll be fully equipped for the exam. So that's it, guys, from us on African Motives. Till we meet again.